Welcome to the Room of Lives. I'm your host, Neil. Today we will hear from Aniket Sanghi, who is getting his bachelor's in physics and astronomy at the University of Texas at Austin and has already begun doing research. He has published work on identifying, photographing, and analyzing different celestial bodies, including planets, using ground and space-based telescopes. Aniket is also interested in science outreach, communication, and mentoring. Aniket gave this talk at Darwin's Pub in downtown Austin as part of the physics department outreach program called Schrödinger's Pints. In this talk, he takes us through several questions. What kinds of distant planets exist outside our solar system, and how are new planets formed? How do astronomers try to find these planets and look for life on them? How can they take photos of these distant planets, and what are the challenges and rewards of this work?
My name is Aniket. I'm a senior undergraduate at UT Austin, and the title of my talk is Photographing Distant Alien Worlds. Okay, so before we look at distant alien worlds, let's look at our own backyard. We have the solar system. So the solar system shows us an interesting diversity of planets. We have the inner terrestrial planets, which are small, have rocky cores and a solid surface. We have the gas giant planets, which are essentially puffy balls of hydrogen and helium gas. And then finally we have the ice giants, Uranus and Neptune, which also are predominantly made of hydrogen and helium, but contain a substantial amount of frozen water, methane, and ammonia. In this set of planets, we have an interesting diversity not only in the composition, but in the size ranges as well, where the largest planets have somewhat formed in the middle, Jupiter and Saturn. So we have the gas giants, the largest planets formed around in the center of this system. We have the next largest, the ice giants, formed further away, and then the terrestrial planets on the inside. So looking at the solar system, we might think, okay, we have two questions. Are there planets outside our own solar system? And the title of my talk was a big spoiler for that. The answer is yes, there are planets outside our solar system. And the other interesting question is, are the planets outside our solar system anything like our own? In fact, when astronomers went out to look for planets, they expected the planets to look exactly like the ones we see in the solar system. And that raises some interesting questions, and the universe actually had a big surprise for us. So I'm going to call upon the NASA Exoplanet Travel Bureau to answer these questions. The Travel Bureau has a set of posters that advertise the different worlds out there, in case you might want to visit one of them. So let's take a few look at a few of them and see what kind of planets we find. Relax on Kepler 16b, the land of two suns. So Kepler 16b is actually a Saturn mass planet that is orbiting two stars at the distance that Earth orbits the sun. It's an actual real-life equivalent of Tatooine, the home of Luke Skywalker from Star Wars. Pretty cool. Experience the gravity of HT 40307g, a super Earth. This planet, HT 40307g, as you can tell, astronomers are not great at naming planets, is a planet that's almost 8 times the mass of the Earth, but is smaller than Neptune as well. So there's no solar system mapping or equivalent of this particular planet. What's sure is that this planet, with its high mass, has a really, really strong gravity. 55 Cancri E. Skies sparkle above a never-ending ocean of lava. So 55 Cancri E is a planet that's twice the size of Earth, but it is 10 times closer to its star than Mercury is to the Sun. So the burning temperature on this planet is enough to melt iron. A hot travel destination for sure. Okay, so within these 3 planets itself, we saw very interesting diversity. And these planets are nothing like the ones we see in our solar system in terms of where they're located, the type of stars they orbit, how big they are, and the composition. And now we have found this zoo of exoplanets, which are planets outside our solar system, that are challenging the way we think about how they form, how they evolve, and how planets actually look like. So, within the zoo of exoplanets, is the Earth special? Do any of these planets have life? And, how can we even begin to know the properties of these planets? Before we answer these big questions, we want to look at how we can actually discover and find these planets. The first method is called radial velocity. When a planet's orbiting the star, it causes the star to also move about the system's common center of mass. So when you look at the light from the star, the light's going to appear with different frequencies as the star moves away from us or towards us, much like how the siren of an ambulance changes in pitch as it moves away or towards us. So this allows us to not only infer the presence of the planet, but also estimate its mass. So that's the first technique. Next, we have transits. The idea behind transits is very simple yet powerful. If you look at the star and the planet edge on, and then view as the planet moves in front of the star, it's going to cause a dip in the light from the star because it's blocking the light. And by measuring this dip, we can infer the presence of the planet as well as characterize the size of the planet. Now you might say, okay, that's great, Aniket. Why are we looking at stars? Why are we going through all of this hassle to look at stars and find planets? Can't we just point a telescope at them and take a picture? And that exactly is the third technique, which is called direct imaging. So here we have a somewhat grainy picture of a star taken by a camera in space. It doesn't seem particularly interesting, but let's zoom in on one of the streaks on the right, on the left. Okay, so maybe we see a tiny point of light here. Let's zoom in further. Okay, so now we see clearly a small point of light. Does anyone want to venture a guess what this point of light is? It's Earth. Yes, exactly. This is planet Earth as imaged by the Voyager spacecraft nearly 4 billion miles away from the Sun, which is this bright star here on the right. Now, I cannot do justice to this famous image, the pale blue dot image that was unveiled by Carl Sagan, in terms of the incredibly humbling perspective it provides us about our lives. But the reason I included this image is to show where we want to go with the direct imaging technique. We want to image Earth-like planets around Sun-like stars and search for signs for life. So I want to go back to this picture because I think it can be a bit misleading. These are all artistic interpretations of what planets look like as they were indirectly detected with the radial velocity and transit techniques. These are not actually how planets look like to us right now. They're more like tiny dots of light, a few pixels of light in the blackness of space. Okay, so the big question. You may be wondering, okay, that's great. Why should I care about photographing a speck of light in the darkness of space? And I would say that directly imaging planets has the potential to answer two fundamental questions to the human race. The first of which is, how did we come to be? So the question of how we came to be depends on the question of how the planets in our solar system formed. Since we cannot look back 4 billion years to our own solar system and see how the planets form, our best bet is to look at young planets around young stars outside our solar system and see them actively in the process of formation, see how they're gaining mass from the gas around in the disk and how they're growing, and determine what kind of planets may be formed by these processes. The second big question is there life out there? And currently Earth is the only planet we know that hosts life, but the search for life is far from over. When you're directly imaging a planet, you're collecting the light that originates in the atmospheres of these planets. By taking that light and passing it through a prism, you can separate out the amount of light at different wavelengths or colors. Now, these atoms and molecules in the atmosphere of the exoplanet that you're studying the light from imprints its fingerprint on this particular light that you receive. For example, in this figure, you can see you have these series of dips from oxygen, water, methane, carbon dioxide, ozone. These dips can allow you to characterize the atmosphere of the planet and search for indirect signatures of life. So this is where we want to go. Okay, so what's the current state of our field? Where are we with discovering exoplanets? This is a plot of mass of the planet in Earth masses versus separation from the star in astronomical units, where 1 astronomical unit is the distance between the Earth and the Sun. Okay, so first I'm going to add 3 solar system planets, 1 from each of the size categories on this figure for reference. So we have the Earth here, Neptune, and then Jupiter. Now we can add all the planets from radial velocity, and then the ones from transits, and finally the ones from direct imaging. As you can see, from greater than 5,000 exoplanets, only less than 50 have been directly imaged. And interestingly, these are all planets that are more massive than Jupiter, but further away in their orbit than Neptune is from the Sun. Okay, and another interesting point regarding our main question is that there is a massive gap here if you want to be able to image an Earth-like planet. How are we going to overcome this gap? And what are the processes and research going on in this area right now? So, exoplanet imaging 101, how do you take a picture of a planet? Imaging a planet is difficult because you need to separate the light from the planet from the light of the star. And this is difficult because the planet is up to 1 billion times fainter than the star. It is lost in the glare of its starlight, much how like a firefly can get lost in the glare of a lighthouse. So can anyone spot firefly in here? No? It's right there. So as you can see, exoplanet imaging is extremely challenging. In fact, it is so hard that this example is not even a true analogy to the problem. The actual challenge is more like if you were in Texas and the lighthouse and the firefly were in California. Crazy, isn't it? This is what astronomers are contending with right now. Okay, so we have our star. We have a little planet next to it that we want to image. It's a little sad because no one sees him. So let's make our efforts and see what we can do. A good first step might be to put out your thumb, block out the starlight, and image the planet. So you can now see the planet's happy. Okay, but there's a problem. Your friend's feeling hot from the sunlight. So they put a fan in front of you that's distorting the air, blurring the image. You can no longer see the planet. So you enlist your trusty friend to place a pair of magical sunglasses that can change itself to correct for the blurriness caused by the fan, and you can now see the planet. And interestingly, this is exactly what astronomers do, believe it or not. The fan here represents the turbulence in the Earth's atmosphere that distorts the images of stars and prevents us from seeing the planets. The lenses here are a system called adaptive optics that can help correct for the turbulence and help us see the planets. And finally, your thumb is an instrument called the coronagraph. So let's look at these in some more detail. So the first step to imaging a planet is to build a telescope and then point the telescope towards a star. Now you need to collect the light from the star. So here we have a video showing the telescope collecting the light. Light is made up of a bunch of waves. So what you do is you want to send this light through a bunch of mirrors, lenses, and finally to your detector, which can image. It's essentially a camera that can image the star. So you get this point source of light with a series of dark and bright rings. This is called the diffraction pattern of the telescope. Okay, so what happens if we if we want to block the starlight? We can use something called a coronagraphic mask, which has a dark hole in the center that blocks the starlight and lets the starlight on the sides pass through. So by placing it at the focal point of the light, you can block a lot of the starlight. But because of diffraction, light can bend around at the edges of that dark hole and still get through. So what you want to do is use something like a washer, which is called a Leo stop, place that in the path of the beam, and now you have removed a lot of the starlight. As you can see, we have a very dark image. And we can now try and see what happens if we introduce planet light. Okay, so planet light comes at an off-axis angle. That is, it passes off-axis from the starlight, it misses the dark pole of the coronagraph, and it passes through the Leo star. So now the planet signal should be visible here. But if we turn off this camera, we don't actually see anything. We see a bunch of speckly features, these are called speckles, that happen because of imperfections in the telescope's mirrors and lenses. As you can see here, the planets, those are the locations of the planets, but you can't see them. So what you do is you use pistons on a flexible mirror, and you push the mirror up and down to correct for the distortions in real time. That's the adaptive optics system. So when you turn on the adaptive optics system and correct for the light, you can get rid of these speckles, and first you can see the brighter of the two planets, and then slowly over time you can see the fainter of the two planets. After some clever processing of this data, you can further reduce the starlight and increase the contrast of the planets and image them. So that's how you image a planet. Okay, a big warning. You're about to see actual images of exoplanets. How many of you have ever actually seen an exoplanet before? Anyone? Okay, few physicists there. You do not count. Absolutely. That's great. Okay, so get ready. Here we have a time-lapse video of 4 planets orbiting the star HR 8799. The star is located at this yellow central point, and this black disk is where the coronagraph is blocking the starlight. And that allows us to see these 4 planets, which are more massive than Jupiter and further away than Neptune is. And you can see this is a 7-year time lapse of the orbit of these planets. And I want to remind you, these are not simulations. These are actual planets outside our solar system in orbit around their star. Pretty amazing. Here's another really cool system, Beta Pictoris b. So, in this case, you're looking at the planet and the star edge on, such that the planet moves behind the star in its orbit for 2 years, it disappears, and then it reappears on the other side after a few years. So this allows us to precisely tell what kind of orbit the planet's following around the star. Okay. So that was great. Now I want to talk to you about planet formation, the birth of new worlds, and how this connects to our question about how we came to be. So let's dive right into this. The planet formation process starts with a massive gaseous disk called a protoplanetary disk around a young star. So let's zoom in this gaseous disk. What happens is that gravitational instabilities cause the gas in the disk to collapse and form a planet. So as you can see, this streak of gas collapsing, and we have a planet there. Now, one of the main observations here is that the planet formed and cleared a gap in the disk. So can we see evidence of these gaps in actual star disk systems and then directly image the planets that might be causing these gaps? So the first answer to the first question is yes, we have disks around the stars. So this is an image of the star PDS-70 taken with ALMA telescope array in Chile. You can see this bright ring of gas and dust around the star. The star is located over here, as well as there's a massive gap from the star to the inner edge of the disk. This is the gap that the simulation was predicting. So are there planets in this gap? Astronomers pointed the largest telescopes, and they found not one but 2 baby planets in the gap of this disk, PDS-70b and PDS-70c. Okay, so let's zoom in on PDS-70b. That's a favorite of mine because it's the first exoplanet that I imaged as part of my research at UT with the Hubble Space Telescope, as you can see here. So it's very close to my heart. Okay, if 2 baby planets weren't amazing enough, there's another secret lurking in this image. Let's zoom in on PDS-70c. So if you zoom in on PDS-70c, you can see the planet here, along with a fuzzy blob of gas surrounding it. That fuzzy blob is actually a disk around the planet that is currently forming baby moons. So we not only have planets that have been formed here, but we are seeing the sites where moons are being formed as well. This system is really a remarkable discovery. Okay, so this was recently discovered just in 2019. And surprisingly, these are the only two baby exoplanets that have been confirmed with direct imaging to date. Surveys of several other stars have not found any new baby planets. So where are they? There is an interesting new system that our group at UT has been focusing on that has yielded some interesting results. So if you would have noticed, the hop-hat viewers in the audience would have noticed that before a gap is cleared in the disk, there's the formation of the spiral arm. Can we see traces of these spiral arms in disks and find the planets? ABR is a star that offers us this possibility. This ALMA image shows huge spiral arms extending out to hundreds of AU. So let's see what we can find if we zoom in. So researchers zoomed in and found a gap in a certain disk around the star. So this is looking very similar to PDS-70. Let's zoom in further on the gap. If you see further in, you can actually see two spiral arms that have been imaged by ALMA again. And authors of this study modeled these spiral arms and said that a planet would produce these spiral arms located at either the location of the white triangle or of the black triangle. So what we did is we took the Hubble Space Telescope and pointed it at these two locations to search for planets. And I hear you ask, what did we find? We found a planet-like point signal exactly at the location of the black triangle. And this happened just last semester, and when the data first came in, I processed it and I looked at the final results. I literally jumped out of my seat and screamed because this was an amazing coincidence, or perfect match of the location. And isn't it amazing how science, when science works perfectly and tells you this story that makes sense? It's really crazy. I can't fathom that. This planet, candidate planet, actually has been published by us over the past month. And I say candidate planet because there are some interesting nuances to this system that need to be studied more to place it at the same level of confidence as the PDS-70 planets. Okay, so I'm going to move on to the final part of the talk, which is the future, what we have in store for you as we move towards hunting for an Earth 2.0. We have a series of ground and space-based missions planned. JWST, the James Webb Space Telescope, has already launched, is delivering exciting results, it's performing better than expected. And two recent results are the detection of carbon dioxide in the atmosphere of an exoplanet. This is the first detection of carbon dioxide made, and it's made by JWST. Another result just came out this past Thursday was the first direct images of a planet in the longer infrared wavelengths. This will allow us to precisely characterize the atmospheres of these planets. So, as you can see here, a panel moving towards higher wavelengths, and this is the planet in wavelengths. Really cool. Okay, we also have the GMT, or the Giant Magellan Telescope, of which UT is actually a founding partner of, and this will be launched, or this will be achieve first light around in 2025, and will push us towards imaging lower mass planets because it is a 25-meter telescope, so much bigger than what we have currently, which is 10 meters. The Europeans are leading the European Extremely Large Telescope. I confused it with the Extremely Large Telescope. But that's slated to launch in 2028. NASA is leading the Roman space mission, which will image a lot more planets from space. And the interesting story behind this is that this is actually an ex-US spy satellite. The defense sector has been keeping hidden until 2012. And you wonder if they had these since early 2000s or even 1990s, what must the defense sector have right now that could change the face of exoplanet science? Okay. Now these missions will help us bridge the gap towards imaging Earth-like planets, but what we really need is a dedicated 10 to 12 meter class telescope in space. And we need technologies like the star shade. So the idea behind the star shade is that you would fly it in sync with the telescope about 4 Earth diameters away to allow the star shape to precisely block out the sunlight and very close to the star, because the Earth is at a very small angular separation. So this is a simulated image of what a solar system like, planetary system would look like as imaged by the star shade in a 10 to 12 meter class telescope. Of course, this is not just a concept, but there's an actual demonstration inspired by origami that NASA is developing this technology on. And here you can see how it would unfold and deploy itself in space. Beautiful, isn't it, what the next generation of telescopes are going to provide? That's great. Okay, so I want to conclude with this slide where I show all the confirmed directly imaged planets as a reminder of what we have achieved to date, and the image of the infamous pale blue dot as a representation of where we want to go next. Thank you, and I can take any questions. Yes?
I was wondering about the star shields, since those are so far apart, do we have a reliable way to communicate between the two objects?
Yes, that's an interesting question, because the main technological challenge with the star shade right now is maintaining that stability and sync between the telescope and the star shade. The star shade is designed in such a way to such that the light would be blocked very close into the star. But right now the question is still unsolved about how exactly you would fly in formation really far away and the kind of orbit you would need to put it into so that it's really stable. So that's still an unsolved problem that hopefully we'll get to very soon. Yes?
So you said that candidate planets that you can photograph when you finish the flags, but that was still candidate planets and some anomalies. What were those anomalies present to be anything?
So the question was, I mentioned that the planet we detected was a candidate planet. Why is that a candidate planet, right? And not an actual planet detection. So the environment of imaging young planets in disks is challenging because the processing algorithms that we use can cause the disk features to, clunk up and look like planets. So what we might actually also be seeing is just an artifact of the processing algorithm. So more observations are needed to maybe use some other indicators based on different wavelengths of light to see whether what we see is actually the signal from a planet and not from, say, light being reflected off the gas in the disk. Yes? Yes, that's great. So carbon dioxide, the question was, what kind of biosignatures do we need to infer the presence of life? So as you saw, carbon dioxide was detected in this very hot planet. So we already know just from the basis of where the planet is located that it cannot host life because it's not in the habitable zone of its star. But to the kinds of biosignatures we need are what I showed in the figure earlier. Maybe if I go back here. We regularly detect water and carbon dioxide, water in the atmospheres of planets. What we haven't gotten to is molecular oxygen and ozone. So these particular features are one of the main biosignatures that we would be looking for, in addition to nitrogen molecules as well. Because nitrogen is, as you can on Earth, is the dominant species, and a lot of activities of life involve nitrogen as well. I'm not a biologist. This is the best of my knowledge about biosignatures. Thanks. Yes.
So these planets, do we have an estimation of their how long it takes them to do their full year, like 1 year for us?
Yes. So the question was, do we have an estimate about how long it takes for the planet to orbit its star? And the methods I described earlier, so transit and radial velocity can tell us about how long it takes for the planet to orbit its star. Because you can imagine, if I observe one dip in the transit event, then after one orbit, the planet is going to come again around and transit again. So there's going to be a second dip. So the time it takes for the dips to occur between them, that's the time it takes for the planet to go around the star lines. Yes, the impact?
Can you detect the presence or absence of the magnetosphere?
Okay, great question. Can you detect the presence or absence of the magnetosphere? Currently, no, but there are there are research programs that are using radio telescopes to try and find planets based on the interactions of particles in the magnetosphere of those planets. So far, those programs have not yielded any detections, but it still remains a possibility moving forward. Okay, thank you. Thank you, Aniket.
Thanks for joining us in the Room of Lives to hang out with the exoplanets. Until next time.